So this little review here, reviewing logarithms, we're going to cover section 5.4 to 5.5a. Your textbook does common log, natural log for 5.4 and 5.5, and then 5.5a does other bases. I'm just going to review them all at the same time. So things that I'm going to cover, what are logs? It's kind of important to remember that, what the common log is, what the natural log is, the properties of logs, when we simplify log expressions, so we're condensing everything down into one log expression, some basic equations with some logs, and then for those of you who don't have a calculator that does this for you, I'll go over the change of base formula. So logs are the inverse of exponents. So I have a little analogy for you. We use logs when we're solving for something and we're not set up to get the answer right away. So in this analogy, if I'd said what's 20 divided by 5, you'd be able to answer that because everything is on the same side of the equal sign and you're told what operation to do. If I said what divided by 5 equals 4, then you might want to think, okay, something divided by 5 equals 4, so what I can do is multiply each side by 5, and I can figure that that number must have been 20. So what this does is it takes the unknown from being part of an expression to isolating the unknown on the other side of the equal sign to make the math a little bit easier. So when we have this question like 10 raised to what power gives me 100,000, what we can do is use our calculator and say, okay, log base 10 of 100,000 equals what? So it runs the inverse operation for you. As long as you're in base 10 or base E, your calculator will do the work for you. Now what we expect you to be able to do is some of these simpler operations like powers of 10 and things like that without evaluating on your calculator. So that's why some of these directions will say solve without a calculator, etc. So our goal overall is to rewrite the problem in a way that you can solve it mentally or be able to use your calculator with a common log or a natural log. So the common log is a log with base 10. This is the one where if you hit the log button on your calculator, it's using base 10. If you don't want base 10, you have to use the log base command under the math menu. Some things to remember with powers of 10. If it's a number greater than 1, the number of zeros is the exponent. If it's a number less than 1, it's the number of decimal places. So like in this case, you have to move the decimal place 6 times to get back up to a whole number 1. So that's 10 to the negative 6. So just in case you needed some reminders on that. So the question we're asking ourselves is 10 raised to what power equals 1? So to simplify these examples, 10 raised to what power equals 1, I'm going to use a question mark as a stand-in here. Because there's no x in the problem, I don't like to invent an x, but you're welcome to use an x if you want. So in order for you to raise something to a power and get 1, you must have been raising to the 0th power. 10 raised to what power equals the square root of 10? Well, it might help you to remember that the square root of 10 is 10 to the 1/2 power. So our unknown here must be 1/2. Now this is a common mistake here. Ooh, I didn't want to do the exponent. 10 raised to what power equals negative 3? So basically we'd need to come up with 10 to some power that gave us a negative number. There's actually no solution to this one because 10 raised to anything, let's say 10 raised to the negative second, well that's really 1 over 10 to the second, which is 1 over 100. So even negative exponents give positive answers. So if you have something in this log situation, the log of a negative number, there's no real answer. We'd have to use imaginary numbers, and we're not using that in this chapter. A couple of other examples now where they're set up in equations, so let's rewrite these as exponential forms. The problem here is our our unknown is on the log side, so we want to use the inverse of logs to get the unknown on the other side of the equal sign. Now our unknown is on the exponent side, so we want to use a log. So this is going to be log base 10 of 29 is equal to x. So we're going to try to figure out what that is, and it's going to be, you'll use a calculator for this one. So you'll type it in exactly the way you see it here. And 4 decimal places is enough. We get 1.4624 equals x. Natural logs are logs with a base of e. Everything is going to be the same as the common log, except instead of writing log base e, we write ln. So to rewrite this, remember logs represent exponents. So e to the 4th is equal to x. So we would evaluate that on our calculator. And we get 54.5982. This one, the unknown is on the exponent side, so we want to use an inverse. So we're going to do log base e of 5 is equal to x. Put that into your calculator, make sure you're using the ln button, and we find the answer to be 1.6094. Some of our properties of logs are very close to the properties of exponents. This is because a log represents the exponent. Because, when we had, this is my go-to example, log base 10 of 1,000 equals 3. So this whole log expression is interchangeable with the exponent. So when we multiply like bases, we add exponents. When we add logs, we multiply inside the log. Because this is an exponent, so they must have been multiplied. Same thing with division. Exponents we would subtract. So when there's division, it's interchangeable with subtraction on the logs. Notice that it gets separated into one log here, and you must have the same base. Power to a power you multiply. So when you have an exponent here, to power to a power, you can turn that into a coefficient, multiplication. Anything raised to the 0th power is 1, so the log of 1 equals 0. When you have a negative exponent, you're going to take the reciprocal, so you can do the same thing here, which makes this the coefficient. And the inverse properties, these ones are pretty useful too. Just like if you have multiplication and division in the same problem, if you're multiplying and dividing by the same number, they cancel out. If you take a log and an exponent of the same base, they cancel out. So this question asks us b raised to what power gives us b to the x? Well, it must be x. And then the log of what would give us log b of x? Well, it must be x. So they kind of cancel out. So we're asked to simplify this all together. I have addition, which is going to turn into multiplication, subtraction, which will turn into division. They're all the same base, so I know I can do all of this. And I'm going to read from left to right. And so I'm going to have x plus 2 times y all over x squared minus 4. And you'll get tricky problems like this. Sorry, base 3. Notice that we can factor a little bit here. these two cancel out, so we really end up with log base 3 of y over x minus 2. And we're going to use some of our log properties to solve some basic equations. So this means e to the second power is equal. So I'm rearranging because I have an x inside the log. I want it on the other side of the equal sign. So once we evaluate e squared and add 1 to both sides, we get as x is equal to 6.3891. You come up with this problem a lot here. It looks kind of like nonsensical. Why do I need this information? But remember that log of 33 can be written as log of 3 times 11, which can be expanded to log of 3 plus log of 11, which means we're going to add up these two numbers. And we would get as our final answer. For those of you who can use your calculator to do the log base, you'd hit math, look for letter A, and I'll say log base. Then you can use whatever log you want. If you don't have that function on your calculator, you'll use the change of base formula. So basically what we do is take this and split it into two logs. We'll use the common log because our calculator can do that. This will be log of 9 over log of 8. The base goes on the bottom, the other one goes on the top, and then you'd be able to calculate that. And we get 1.0566. You could do this with natural logs and it would get you the same answer, which is kind of weird because one's base 10, one's base e, but exponentials and logs are all about ratios between numbers, not the distance between the numbers. Alright, that's it for the review of logs. If you still have any questions, you'll get opportunities in class to ask me, but please, make sure you're referring back to your notes as often as possible.